PhD defense of Javad Amirian. So I will first begin to present the member of the jury. So I begin with the two reviewers. So Professor Dinesh MANOCHA from University of Maryland in the United States, and Professor Alexandre ALAHI from the École Polytechnique Fédérale de Lausanne, EPFL, also. Nuria PELECHANO, professor at Université Polytechnique de Barcelone. Frédéric LERASLE, professeur at Université de Toulouse 3, Paul Sabatier. And the two supervisors, so Jean-Bernard Hayet from CIMAT in Mexico, and Julien PETTRE from INRIA in Rennes, and myself, Éric Marchand, professor at University of Rennes. And that's all. So Javad, you have 45 minutes to present your work, and after we will ask you some questions.
Yeah, thank you very much, and hello everyone, and welcome to my PhD defense. Thank you to my committee, Dinesh, Alexandre, Nuria, Frédéric, and also Eric here. And I'm honored to have you on my PhD committee. So thank you to my friends also, and everyone that on YouTube may be following this PhD defense. So today I will present for you my PhD research, which is about human motion prediction for robot navigation. So robots are actually entering more and more into our societies and share a space with humans. We have no robots that are able to deliver goods and packages or take care of elderly people and socialize with them. And some are changing the transportation and mobility technologies, such as self-driving cars and autonomous wheelchairs. So in all of these applications, robots are more and more engaged in dynamic environments. This means that the traditional sense, plan, and act paradigm that were used to control the robots in static environments has to be updated with a prediction component to predict the motion of surrounding objects in an environment. So this component becomes even more crucial in the scenarios where humans are also engaged, in human populated scenarios, where there is human safety concern, and also the robots should show socially compliant behaviors. So this motion prediction problem can be done in different forms and at different levels of detail. For example, we might be interested in doing the trajectory prediction or doing the prediction for the human pose and gait. Or we can also make short-term or long-term prediction. But in this thesis, we have addressed the problem of human trajectory prediction, or HTP, which is crucial for the robot navigation. And to be clear, we're talking about predicting the future locations of multiple pedestrians in an environment for the next 5 seconds or so, given their past motion trajectories. So to address this problem, we need to know that the motion of a pedestrian can be impacted by multiple different factors, from physiological factors like weight or height of the pedestrian. The cultural factors or the personality of the pedestrian can also impact. Then there are environment factors. The presence of obstacles, the type of the environment or the surface can also influence the motion of pedestrian. And also, we know that humans are interacting each other in an environment using some social rules. So we need to also consider the social interactions between the agents, like collision avoidance, grouping behavior, or leader-follower behavior. And also, we know that human motion can be multimodal in nature. For example, a pedestrian at an intersection can have multiple paths to choose. So the HTP problem is a complex and challenging problem. So let's together take a look at the related work and the state of the art. So taking a look at the literature, we see a broad range of approaches, right? From constant velocity to more recent neural networks or reinforcement learning algorithms. So to better understand the relationship between those approaches, we have proposed a taxonomy. In this taxonomy, we have one dimension to express to which level the model is driven by data, or on the other hand, by expert knowledge. And on the horizontal axis, we have the horizontal axis represent the level of stochasticity handled by this model. From left hand, we have deterministic models, and we have also at the right models that can deal with complex probability distributions. So let's start with dynamic model or explicit dynamic models, such as constant velocity and some of its variant. So we know that they are mostly deterministic and knowledge-driven approaches. And they are too simplistic to make predictions in complex and long-term settings. But they are still good baselines for comparison with new methods. We have also crowd models that are mostly also knowledge-driven and deterministic. So they model interactions between agents, and they are usually used for local navigation. Based on a survey by Fantol and PETTRE, we can classify these models into 4 categories. We have force-based models, such as social forces model, which handles the obstacles and the goals in the environment with repulsive and attractive forces. We have also velocity-based models such as RVO, which is a very popular model in robotics. And in this model, the agents make a linear prediction of the surrounding agents and construct the set of velocity obstacles, and then find an optimal velocity for each agent among a set of admissible velocities. We have also some vision-based algorithms in this family here. They usually try to mimic the visual navigation of humans and are kind of more computationally expensive. We have also some data-driven crowd models, such as this work, which is called crowds by example. And the idea is to find the nearest example of interactions between agents in a database of examples and use this example to simulate or predict agents. So again, the problem with this family of models is that they fail to provide good predictions for crowded settings, for complex crowded settings due to use of handcrafted models, handcrafted rules. So there are also planning-based models that are mainly knowledge-driven. And the principle here is to estimate the goal for each pedestrian and then find the best trajectory to reach those goals, usually by optimizing some cost functions, such as the shortest path or, such as shortest path or maximum safety, and so on. So next, we have some reinforcement learning algorithms here that are recently becoming more and more popular in robotics as well. So the principle here is to learn the policy or the behavior for an agent by maximizing the reward obtained from interactions between the agent and its environment. Right? So they can actually fall into all of these 4 categories here. We have standard RL models that use more handcrafted reward functions. We have inverse RL that are more data-driven and learn the reward function from data. And we have also some imitation learning algorithms such as GAZE that are both generative and data-driven. One problem could be with this family of models is that most of the models that we know in this category still use handcrafted reward functions, such as avoiding collision or smoothing trajectories, or we can have some dimensionality problem with these works. Finally, we have statistical pattern-based models at the top, ranging from deterministic to stochastic. And the main motivation here is to make benefit of large crowd data sets for predicting human trajectories. Many of the works here are based on neural networks or deep learning, where the idea is to encode motions and interaction between agents through the layers of a neural network. So we know that social LSTM is one of the most popular works in this domain, which invented a new pooling mechanism for integrating the hidden representation of the neighboring agents and using this pooling mechanism to learn the social interaction between agents. The problem with social LSTM is, however, it just handles unimodal trajectories. Next, we have generative models that can be a solution for handling multimodality problem, right? For example, we have GANs, or generative adversarial networks, that are able to learn the distribution of the data. They, together with other generative models such as variational autoencoders and the flow-based models, are able to learn the distribution of the trajectories and deal with multimodality distribution, actually. So the principle in a GAN is to generate a set of plausible trajectories using the adversarial loss, which is obtained by solving a minimax game between a generator and a discriminator. Usually, it's like generator tries to fool the discriminator by making samples similar to the ones in a database, and at the same time, discriminator tries to not be fooled by identifying fake samples from real ones. So social GAN is, let's say, the first GAN model that were applied to predict the human trajectories. But the thing is, it suffers from mode collapse problem, something that I get back to it in a minute, and I will explain. So here we can analyze the related work and put our contributions. So looking at the solutions above, we can guess what are the research trends, right? A lot of research is toward data-driven models, usually using deep learning, that are trying to handle the multimodality problem. And at the same time, we see a kind of trend toward reinforcement learning algorithms to improve the generalization. But there are, as I said, few gaps and some questions to raise here about the multimodality in the prediction models. We can ask that, are there better ways to preserve the modes of the data, and how to evaluate a multi-answer prediction system? About assessment of existing trajectory data sets, we can ask that, are we using the right data to train and validate our model? And also, will human behavior change in presence of a robot or not? And also, for handling the prediction from robot perspective, we can ask that, what if there is some imperfection or occlusion in the perceived crowd, right? So to address these questions, I worked on a couple of ideas during my PhD that I will present in the following. The first research that I worked on is about benchmarking trajectories dataset, that we call it OpenTraj. Social ways is our proposal for handling multimodality problem in human trajectory prediction. Also, another research was done about handling crowd occlusion and reconstructing the occluded crowd. And then I will give a brief presentation about our joint work with UCL on a crowd-robot interaction experiment to study the impact of robots on crowd. So let's start with OpenTrack. So to address the problem of HTP, or human trajectory prediction, a lot of research has been done to propose usually new models, new approaches. And in parallel, lots of effort also made toward making benchmarking those algorithms that has led to creating several trajectory datasets. But here an important question to ask is how to measure the complexity or difficulty of a data set for the task of prediction. So, because we know that these data sets are recorded in various situations and with different properties that are planned by dataset creators, such as duration, the location of the recording, the sensor type, the crowd density or activity, and so on. Also, there are some hidden factors, let's say, that are not under full control of the dataset creators, such as the variations of the trajectories, the multimodality in the dataset, the nonlinearity, agent interactions, and so on. And above all, there is a prediction complexity variable that can be impacted by all of those factors. So, to measure this complexity, we presented multiple indicators in 4 different categories to measure different properties of datasets. For example, for a spatial analysis, to measure the predictability, trajectories regularity, and also to measure the context complexity, which is composed of collision energy indicators and crowd density indicators. I will present in the following some of them. But before we proceed, we need to know that some of these indicators are applied on motion primitive that we call trajelet. Actually, a trajelet is a piece of trajectory with a fixed duration of 5 seconds, and some of those indicators are applied on them. So, in the right, you can also see a snapshot from a Stanford Run dataset with 6 trajects from a trajectory. So to measure the predictability of a traject, which is one of the indicators that we propose, we use the conditional entropy formulation. It can be interpreted as the predictability of trajelets x plus that come after a given trajelet xk, right? So for this, we define a Gaussian kernel to measure the similarity between a pair of trajelets x and x prime, and then we approximate the conditional density with a Gaussian mixture model, as you can see in step 2 here. And finally, we can estimate the entropy of the trajelet using a Monte Carlo sampling. So the thing is, lower entropy values means that the trajelet xk will be more predictable. For example, in the right example, you can see the trajelet x2 is sort of outlier trajectory in the ETH dataset with the lower entropy value, which means is more predictable than x1, which is a straight line and can be followed by a more diverse set of trajectories. For measuring the trajectories regularity, there are another group of indicators that we proposed. For this, we studied motion properties such as speed and acceleration variations, and also indicators for measuring the nonlinearity of trajectories, such as the path efficiency and the angular deviation from linear motion. So in the right, you can see two examples for the path efficiency. The one at the top is from ETH dataset with path efficiency around 99%, almost very linear, and the one from Hermes dataset with 90% of efficiency. In the bottom, you can also see the angular deviation from motion, from linear motion for the two datasets, and you can see a quite meaningful difference between those. So I will mention here some of the key findings that we found during this research. So the first is that most of the trajes are very linear. The path efficiency of many of them is, most of them is more than 92%, and many of them are even more efficient than 99%. This could be a sign of imbalanced data in HTTP dataset. And we can conclude that the displacement error metrics cannot be efficient to evaluate trajectory datasets, trajectory models, trajectory prediction models, right? So for the context complexity, as I said, we measured the crowd density indicators, and we observed quite meaningful differences across datasets, but at the same time, it was not obvious that it can translate into different collision energies among different datasets. It means that we have almost the same level of collision energy across those datasets. Regarding the predictability, we see again a lot of similarity across different datasets, but still, this study and these indicators can be very useful to improve the selective metadata sets, such as TrajNet++, that separate complex samples from simple ones. So now that we have studied the HTTP datasets and their properties, let's present our next work, which is social ways, where we proposed to handle the problem of multimodality in trajectory prediction. So social ways are proposed prediction model based on GAN, where we had three principal designs: to be data-driven, where it was achieved by using neural networks, to handle the multimodality that were achieved by using GANs, which is a generative model, and also to handle the agent interaction, that we did it by using some handcrafted social features that I will explain. As you see here is the architecture of the model. In the left, we have the trajectory generator. I hope you see the pointer. And in the right, we have the trajectory discriminator. Again, as I explained, there is a game between the generator and the discriminator. The generator tries to make predictions similar to the ones in the database. And the discriminator tries to identify between the fake and real samples. And by this training, finally, our generator would be able to learn the distribution of the trajectories. Let's have a closer look at the predictor or the generator network, where we use LSTM blocks to encode the trajectories. We, in parallel, use we define three social features, including Euclidean distance, the bearing angle, and distance of closest approach, or DCA. This third one is a concept coming from the biomechanics, and roughly represent the probability of a collision between two agents. And we apply some attention pulling on top of these features and encoded trajectories to assign importance weights to each interaction, as you can see in this figure here. And at the end, we decode those latent variables with another LSTM log. So another problem is that mode collapse that I mentioned before. Because as we know, GANs are prone to the mode collapse problem, which means that they only characterize a few modes in the distribution of the data. Like what you see in this example here, where the distribution P of X is estimated by two distribution Q1 and Q2, and both of them have sort of mode collapse problem. In some applications, such as face generation, maybe that's not a big deal to have some mode collapse, because still we can make some nice faces. But in our case, which is a trajectory prediction problem, and it will be used for the navigation of the robots, it's quite essential to not miss any modes of the data. Actually, there are attempts to remedy this problem, including the unrolled GAN, which was an idea to stabilize the training between the generator and the discriminator. And also the Wasserstein GAN to deal with the problem of vanishing gradient. There was also another work called InfoGAN that we leveraged in our work, where the idea was to use the information loss. What is this? We maximize the mutual information between the input of the generator and its output. But how to do it? We define a new input variable to the generator, which is called the latent code. And also we add a new loss function to the training, which is the mutual information between this latent code and the X. Actually, there are some technical details here that I will skip for the sake of time, but we can get back to it at the question session. So for the evaluation, before I report experiment result on real data set, we created a trajectory data set to evaluate how a prediction model deal with multimodality impact. So here we have K groups of observations in blue that are followed by M set of predictions in 3 uniform branches. Here you can see in red probably. And the task is that given one observed trajectory with a length of 2, generate n predictions. We compared versus other baselines, including the variety loss in social GAN and also the unrolled GAN that I just explained. And InfoGAN is the idea that we use in our model. So here you can see the qualitative results across different iterations, training iterations. As you can see, the proposed method using InfoGAN is able to learn the modes of the data across different training iterations compared to other baselines such as vanilla GAN, social GAN, and so on. So also to quantitatively evaluate our method, we propose 2 evaluation metrics. One is a Earth mover distance. Actually, this one is to measure the minimum amount of work that is required to turn one distribution into another one. And the second metric that we use is a 1 nearest neighbor classifier that tries to figure out how far the real and the fake samples are distinguishable. You can see here, for example, an example where the red samples, which are, let's say, the generated samples, has not converged toward the ground truth samples or the real samples. And the accuracy of this this type of example would be something around 100%. And also in the left, we have something like the generated samples are quite almost copies of the real samples, and the accuracy will be something around 0%. So these are not desirable. We need something like this where the real and fake samples are not distinguishable anymore. So that's why we desire a model with a 50% of accuracy. Here are the results across different iterations. As you can see again, the proposed method using InfoGAN is giving better result in terms of one-on-one accuracy and also the distance to the ground truth distribution. This is the black curve that you see in both figures. All right, so about evaluation on real data sets, and so we use average displacement error and also final displacement error, and we evaluated on ETH and UCY datasets, kind of two very popular datasets in this category, in this task. And let's say at the time of publishing our work, it outperformed some of the state of the art, including social LSTM, social GAN, SOFI, and so on. Also in the bottom, you can see some of the qualitative examples where the predictions of the social waves are shown by purple color, and yeah, you can see the distribution of the generated trajectories actually. Here is also where we applied our trajectory prediction GAN on the for the simulation of the crowd, where we used a GAN to generate trajectories, and we integrated this with a path following algorithm and also a collision avoidance algorithm to simulate agents in an environment in a data-driven manner. So far, we tackled the prediction problem, assuming that the crowd is fully observable. But that's not the case when we work with robot perception, right? So here is our next contribution that we call crowd imputation to deal with occlusion problem and to predict or impute the occluded crowd. So actually, due to low height of the robot sensor, there might be noticeable occlusion in the crowd, right? To understand the extent of this problem, imagine what will happen if we replace one of the pedestrians in such crowd, this one, with a robot. So we did the simulation, we replicated the crowd, and we simulated the robot in this crowd and also its LiDAR sensor. And here is the output. So as you can see, on top of this LiDAR sensing, we run a detection algorithm, and we realized that a lot of pedestrians here are being occluded, those which are shown by the red circles. So we created this problem that given the robot observations about the crowd, what is the probability of presence of a person at a query point XQ, let's say at occluded areas in this environment? And to answer this question, our proposal is to use the structures and patterns in the crowd. And as we know, a crowd has different properties, such as the type of the flow, the density of the crowd, having the groups in the crowd, and also the size and shape of the groups. So we introduced the notion of social ties, which is simply a displacement vector between two agents expressed in the local frame of the first one. And having this very basic primitive, we can build up more complicated patterns actually. So we classified even this ties into strong ties and absent ties to represent the long-term interactions versus transitory interactions. The first group include the grouping behavior, leader-follower behavior, and so on. And examples for transitory interactions include collision avoidance, overtaking, and so on. And the classification rule was quite simple, using some maximum distance between the two agents, maximum variation in distance, and the orientation between the two agents. We also defined a community, or let's say a group of pedestrians that are connected by strong ties. Here you can see an example, for example, in Hermes dataset in a bidirectional flow. One flow is going to the right and another to the left, and you see two communities. And also another definition, territory, which is defined as all the locations close to a community using a distance function. So in the right, you can also see the territory for this group of agents or this community. This one in red and blue, small circles in the background, right? So using these territories, we can also make our prediction algorithm. So here is some detail of the imputation algorithm, let's say, to estimate the probability of presence of a person at a given query point X. Here are actually some technical details. I can skip for the sake of time. We used the marginalization over the visibility values and for different communities. And then we also used the extracted distribution of the social ties, the strong ones and the absent ties. And then having this equation, we can estimate this probability for a grid map like this one around an agent. And then once we have this probability distribution, we can iteratively sample from it and make the imputations or predictions. Here is an example where you see here is the robot or the agent that has perceived the environment, and the red pedestrians or the predicted locations of the agents that I will also give an example in the following. So we also extracted social ties from multiple crowd data sets and computed the polar histograms for strong ties and absent ties separately. So we observe actually different crowd patterns from different data sets. Here is an example. Here is the one from Zora dataset. As you can see, we observed some side-by-side group behaviors in this dataset. But here in the Hermes dataset, in a bidirectional flow, we observe more leader-follower behavior. And also in the ETH dataset, we see a mix of both behaviors, the side-by-side groups, and also here, the leader-follower behaviors. So some of the experimental results on this proposed algorithm. So we evaluated on 3 datasets, Hermes, ETH, and UCY dataset, and we measured the mean square error, or MSE, over the occupancy map between the ground truths and the predictions. We actually used 2 baselines. The first one is a where there is no prediction, something that we call it a vanilla MOT, or multi-object tracker, let's say. And another is using PCF, or reconstructing using pair correlation functions. This is something more used in computer graphics for painting the pictures, let's say. So the results actually, so we got interesting results on Hermes dataset where the crowd has more structure and has higher density. But the proposed algorithm couldn't improve the baselines on ETH and UCY datasets, where are kind of less structured and has low to mid-level density. Here we can see in the bottom the error over different density values, crowd density value for the two datasets, for the Hermes one and for the ETH one. And you can see the error for the blue curve line, which is the proposed algorithm is better for the case of Hermes, let's say. Here you can see also an example of the imputation. There are some more examples that I will skip now, but we can see together later. So this is our final contribution that I will present, which is a crowd robot experiment that we did in collaboration with UCL to study the impact of the robot on the crowd. So the motivation was that a lot of existing data set neglect the fact that there is no robot in the crowd, and they train and evaluate their model on data set where there is no robot. So we did this experiment with UCL in the Pamela facilities in London. In this experiment, we asked 28 participants to do a gate crossing scenario. We repeated this experiment with different configurations, with a case where there were no robot, or where we have the PETTRE, the human robot in the crowd, and also with a semi-autonomous feature in the crowd. So we evaluated multiple factors to measure the robot effect actually, including the evacuation time, order inversion rate, the local density of the crowd, the pedestrian speed and acceleration around the robot, and so on. And again, some of the key findings here to share with you. We realized that the evacuation time significantly increases when a robot was involved. And also the order inversion was significantly different for the case where a PETTRE robot was engaged versus the case of the wheelchair. As you can see, 86% of the pedestrian overtook PETTRE, almost no care for the PETTRE. And on the other hand, only 37% of the pedestrians overtake a wheelchair. So kind of more respect or something like this for a wheelchair or an autonomous wheelchair in a crowd. So here you can see the difference that is made by putting a robot or a semi-autonomous wheelchair in a crowd. Right. So about conclusions and future works. So in this PhD, we proposed multiple scientific and technical contributions. First, we proposed a set of meaningful and interpretable indicators for analyzing HTTP datasets. And in the light of this study, new data sets, benchmarkings, and evaluation methods can be designed. In the future, we can find a correlation between those indicators and remove the redundant ones. And also, we can consider the impact of the context on predictability of the trajectory. We also improved mode-preserving capabilities in GAN-based prediction, and also used two new metrics to measure the quality of predictive distributions for this task. In the future, we have to work on learning disentangle representation for social interactions, and to design models with more generalization capabilities, maybe with more different a set of various data sets and using a lot of data. We also consider the problem of crowd prediction from a robot perspective and propose an algorithm to predict the occluded crowd in a structured and high density crowd. So in the future, we suggest to use machine learning algorithms to extract complex patterns from crowd to handle less structured scenarios. Also, we can integrate with trajectory prediction systems, which is another application. I mean, it should be integrated with trajectory prediction systems. Also, our final contribution, the crowd-robot study, that crowd-robot interaction study that we conducted with UCL. It was kind of the first controlled crowd-robot interaction experiment, where we provided new insights about the impact of the crowd and also the type of the robot on a crowd. In the future, we expect to see large-scale experiments like this with different robots and with different type of scenarios. I think I should stop here, and we can have some conversations during the questioning session. Thank you very much. Here is the list of my publications, and thank you very much for your attention.
Merci, Javad. Thank you. So now we will have the questions. If everybody is still there, I hope. So we will begin with the people who are far away from us. So I will begin with Dinesh MANOCHA, professor at University of Maryland. Dinesh, if you heard me.
Sure. Can you hear me?
Yeah.
Good. So, Javad, nice talk. You have a lot of cool stuff here. The last part you talk about robots and some results on paper. Did you look at the effect of these method user studies when the density of the people may change? From what I could see, the scenarios appear to be rather sparse. What would happen if if a robot goes to a slightly more dense crowd, and that's where prediction become more important?
Actually, I would say the scenarios were sort of high density. I mean, if you want to look at the local density, not the global density in all the environment, but if you measure the local density, of course, we have a lot of high density samples here. But again, if we didn't test with other scenarios with higher densities, of course. But again, so let's say the key findings, again, going back to the key findings, were that we showed there is a difference where a robot is engaged. And this is a very important point to make, right? And of course, it was kind of obvious but it has to be shown in some experiment. And on the other hand, the type of the robot that we show that is also important. So those are the key findings that we found, and maybe in the future also you can do other experiments to find with other density, crowd densities, with other scenarios, and a lot of different scenarios.
Yeah. See, the thing is, even when humans walk, we sometimes we do long-term anticipation or long-term planning, and that's where density global matters. This is one. The other question was with GAN. You show this, the learning aspects. You show some promising results, but do you see any limitations of what kind of characteristics you can or cannot learn with GANs? Do you have any feeling on that?
All right. Actually, a lot of problems with GANs. And as you know, this work we did in 2018 and published in 2019. And after that, lots of other generative models were proposed, including variational autoencoders, even flow-based models, right? So in my point of view, they did a better job than GANs. GANs, as you know, also suffer from a stability problem. The training is very unstable, and they a lot of time do not converge, and you need to do a lot of playing with the hyperparameters to make it work. So yeah, a lot of problems with GANs. If I want to continue on this line of work on multimodal prediction, I pick other models, actually, not GANs. A lot of difficulties I faced, and I feel other models can do even better.
Okay, thanks. I'm okay for now. Thank you.
Thank you very much, Dinesh.
Okay, thanks. We go now in Switzerland with Professor Alexandre ALAHI from EPFL.
Thank you very much. I hope you can hear me well. First, I want to also congratulate you, Javad. Fantastic work, presentation, a lot of exciting ideas. So thank you. Thank you also for involving me in this thesis. I enjoyed a lot listening to you and reading the thesis. I do have a lot of questions. I'll try to be fast and not take too much of everyone's time, but it's also because of my own personal excitement and interest. I'll go by order, and some of you already talked about it in your future work direction, but I just want to maybe still have a discussion with you. The first one is on slide 23. I think when you present this measurement of complexity with entropy, and indeed, I think you're studying predictability based only on the past trajectory, I believe, if I'm correct.
Right.
And we know that I mean the main excitement of human trajectory prediction is because of the interactions, and we might actually be extremely predictable if we do a good job in modeling prediction interaction. And so how would you so how do you see this being addressed?
Right, very good question, Alexandre. So yeah, this was something that we can think of. Actually, so as you can see in this formulation here, we compute this entropy condition on just the observed trajectory or the trajectory of one person, right? So we can also condition it on other variables. let's say, the interaction that you mentioned. Let's say we have.
Yeah. So why haven't you done it?
So why haven't I done it? So let's say we started this this work, and let's say we started to evaluate the trash list. And of course, it can be done in the future. I have not worked on all the problems, of course, and I have not solved all the problems. But it can be a very interesting direction for the future.
Okay.
One comment I can make here is that, you know, last year there was a paper, Transformers for Trajectory Prediction, if you remember that.
Right.
That work.
Yeah.
In that work, their model didn't use interaction at all for predicting the trajectories, and they all almost did a good job on the TrajNet benchmark. They did a very good job. They were on the top of the leaderboard. So, I mean, even without considering the interaction, there can be some predictability, some prediction model. So this is to make here, this point to make here. Again, you're right. Social interaction play a very important role here, and it can be done in the future.
Okay. Thank you. I guess since you talk about that line of work, and one answer to this, the fact that this transformer network that was able to do a good job in just using history is of the bad job of the community, and myself included, of sampling trajectories that turn out to be linear or not necessarily exciting statistically with respect to social interactions. And that's why we did TrajNet++, where we focused on interaction and non-linear behavior for the evaluation. Have you actually studied social ways on TrajNet++, or was it a reason to not do it?
Well, it should be done actually, but I mean, so at some point during my PhD, I started working on two other problems in parallel. As I explained here, the occlusion problem that I explained, and this experiment with UCL. So maybe that was a matter of time, but of course, I really appreciate this TrajNet++ work that we have done with Parse, and also with OpenTraj. We try to, as I just explained here, to make some meaningful indicators that can be useful for improving TrajNet++. But you're right, a lot of experiment could be done here.
No, I also think that you did social ways way before we released TrajNet++. But I'm wondering if your code is available, or how difficult will it be to be able to run your algorithm on it as a future work, maybe, or for someone else to do it.
Sure. So one of the things still has to be done during my next 2 months stay at INRIA is to integrate the social ways on our CrowdBot project actually. So
awesome. Okay.
This is some phase we have to do still, and I hope we can do some evaluation on TrajNet++ as well.
Awesome. And I think you also talk about it. I love your metric on OpenTraj, and I had this question of how do they relate with the performance of these method on the other metrics. So we see that when we look at the average displacement error across these different data sets, the numbers are in a different range for all methods. do you see this a direct link between your metrics and this type of ranking of the methods on these data sets?
Not honestly, we didn't do this experiment. As I mentioned, in the future work, there can be some work to find a correlation between those things. It should be very interesting to do this, but I totally agree with you on the point that, as I just mentioned, in the key findings of OpenTraj. So we realized that a lot of trajectories are highly linear, as you just pointed out. That's why still with a constant velocity model, you can do a very good job with something like transfer model. Yeah, that's why right. This OpenTraj was helpful to give insight that ADE and FTE metrics are not doing very good to evaluate prediction models.
Right. Yeah. On slide 30, you have this nice toy example to compare multimodality, and this is a question that I also challenge all my my researchers is. So when I look at your methods, like vanilla GAN and all these things, it's, yeah, I guess, how do you know that it's not an issue of training and hyperparameter search for some of these baselines?
Right. You know, the thing is, I can agree with you up to some degree, right? GAN is very tricky to train. You can do still a good job with vanilla GAN. Here, the point was that we did it with the same set of hyperparameters, and we obtained this result. But yeah, you can play.
So
with
you did not.
parameters.
But you did not try to find the hyperparameter for each of the model. You use the same across all the models.
Yeah, this is what we did.
Okay, so that potentially can be challenged, right? So each model maybe should have its own hyperparameter.
Well,
right?
if you just let's say all the rest of things are equal, the model is equal, similar, and only the thing is just adding this loss function on top of each other. Maybe you're right. The lambda parameter, or let's say, I don't know, the training parameters such as the learning rate or so on can be played with. Still different result. Yes. I mean,
No, but yeah.
Right.
Okay. No, but yeah, that's still very interesting. Yeah, thank you. Slide 33. Also, this is a common challenge that we have faced in the community. So when you compare to these other methods like SOFI, SGAN, social force, linear, do you compare by running the algorithms on the same data as you have, or you just use the numbers from a previous paper and add your numbers to these?
Yeah, honestly, or let's say for social LSTM, at least I remember that we just picked the numbers from the paper. For the social, again, it was there. We used the model, linear, yeah, it was done.
But
yeah, but
so
for some of the models, honestly, we just picked the numbers from the paper, right?
But the challenge is that you guys, I mean, nobody has the same data. So even if we claim it's the same data set, we're not sampling the same trajectories. And as we all know, the way we sample, we can end up having a lot of linear example, and they're from the same data. So how can we So, yeah, I mean, isn't it dangerous to not use the same data?
You're right. You're right. A very honest point to make here is that look at the numbers. Even a linear constant velocity model is doing a comparable job with very sophisticated models. So that's why I don't really like to push on these numbers too much, let's say, on AD and FTE. And I think you're right. This is maybe not the best way to compare with baselines, but maybe also we have to think of a standard benchmarking such as Trajectory++. That's a very nice benchmark. And yeah, every model can just run on Trajectory++, and we have numbers can be very clear to compare with.
Yeah. And so I have one last question regarding the robot crowd experience, which is indeed something that we all need, and it's extremely appreciated that you guys are doing it. The first thing that when I look at your videos that kind of surprised me, or one is how are you controlling the robot? Is a human with a remote control that is controlling, or it's an algorithm?
For the pepper, no, it's just remote control, let's say.
So because to me, I could definitely see the behavior of the robot to not be very realistic. And me as a human, when I see it, I will maybe not be comfortable and indeed change my behavior because I don't think the robot was able to do a realistic navigation. So how can you make sure that this is addressed when you run this type of experiment? Or if maybe you train your driver of the robot, or at one point your conclusion might change, right? With respect to the paper.
Very good point. So this experiment was done in a scale of like 2 hours of experiment with less than 30 pedestrians. I want to just I want to give some context. And it was quite costly. It costed us like, for each person we had to pay like 30 pounds or something to hire them for 2 hours and do the experiment. We need a lot of experiment with different robot navigation scenarios, with different crowd scenarios. All of those factors are important. Also, if you continue this experiment for more 2 hours, I'm not sure you get the same result. Maybe people get more comfortable with the robot, right? So that's why, yeah, it was an interesting experiment, but we need to find a way to do a lot of similar experiments like this.
Because you guys want to publish, I mean, I don't think this line of work has been published yet, right?
This is just, we got
the beginning, no? Oh, you got accepted?
It was accepted. Yeah, it was accepted to Soro, which was IJSR. Yeah,
okay, cool.
And will be published quite soon.
Oh, okay, awesome. Congrats. Because I feel like yeah, I mean, to me, I mean the conclusion are indeed intuitive, but they're related to navigation, but also the robot size. So I mean, what you mentioned about the wheelchair, it's much bigger. So I mean, obviously the aerodynamic will be different compared to paper. So that's why I was to to me was a very difficult. It's a difficult actually design, experimental design, to be able to say something more than that and potentially surprising, that we would not expect. So that was but no, it's already a great step. So thank you for all these answers and discussion. I let the others ask you a question. Thank you.
Thank you very much, Alex.
Thanks, Alex.
Thank you.
Thank you. So we now go in Spain with Nuria PELECHANO, professor at Technical University of Catalonia, Polytechnical University of Catalonia.
Okay, thanks.
Nuria?
Yeah, can you hear me?
Yeah.
Okay.
Yes.
Okay. Actually, I think I'm gonna change the order of my questions to continue with the issues that Alex was talking about. But first of all, I would like to congratulate Javad because I think it's a really nice work. You've tackled a very difficult problem from different perspectives, both from the robot point of view, from the human point of view around robots and predicting trajectories and creating trajectories for robots. I think it's really interesting topic. And the thesis is also very well written. It's a nice read, so congratulations on that. And I start now with the last chapter, actually, so I continue with the questions, because I think it's very interesting, the experiment on how humans behave around robots. And there are several questions that I don't know whether you haven't thought about them yet, or they're in the future work plans. No? So, for example, I really like the results you showed regarding how people behave around the robot and how people behave around the wheelchair. And I think a very important aspect for those differences in the behavior are given by social rules, things we learn in society. So, for instance, when you see a person in a wheelchair, society tells you the way you have to behave with them. No, you're meant to give way and you're meant to help them. Whereas with the robot, we don't have any social rules yet. We are not familiar with them yet to that degree. So, do you think that in the near future, or as people become familiar with this kind of robots, these results you obtain now could change massively based on social rules that will appear in the future, for example, and how that could affect your the overall behavior of the crowd?
Right. If I understood very well, because I have some noise from your voice, your question was about adaptation by people for something like pepper, right?
Right. As we get more used to be surrounded by these type of robots, because at the moment we don't typically see them in the street or anywhere, so we don't really know how we are meant to behave around them.
This is a very nice question, and the people that we asked for, the participants that we asked for doing this experiment. So we run each of those scenarios for almost like 5 repeats or 5 iterations. And during those 5s, the first time that a person sees the pepper, maybe it could be a little strange. The next time, get used to it. In just like 30 minutes, there is some curve and a little difference in the behavior. But you're very right. I mean, once people have lived with pepper for like weeks or months, their behavior, of course, would change. But I guess still the point that we made, that was the comparison between wheelchair and pepper, could still be valid to some extent. Maybe the same argument that you said. We have some respect for a person on a wheelchair, but even when we used to see pepper on our beside, I mean, we don't take care about it. So, I mean, there will be, of course, some change, after adaptation by people, but still those points can be valid. That's my point.
Okay, because you were mentioned how as the experiment goes by, people learn a little bit and get familiar to PETTRE. So I imagine after years of seeing those little robots helping in different tasks, we might change a lot how we behave around them, or even give them like human traits in a way, just like some people love their cat so much they almost treat them like a human. I think it's something that there's been a bit of investigation already that it can also happen with robots to a certain extent, no? As you become familiar with them.
Right.
So that's I think it's a really interesting topic, and I'm sure you will be able to work on that even more in the future.
If we can afford the money, yeah.
Okay, that's fair enough. Okay, so then I'll go back to the issue with predictability and how you decide what to use as a measurement for predictability. No, in your work you're using conditional entropy, and you've showed these nice results on how this conditional entropy helps you to determine how predictable a trajectory is. I always have the feeling, and correct me if I'm wrong, but when we talk about predictability, it's sort of, we end up with measurements that sort of tell you how straight the trajectory is, that it's as smooth as possible, that it doesn't have abrupt changes and things like that. And this is very nice and easy to use because you can predict the next positions relatively well. But in my opinion, a person walking doing zigzag, let's say you see a drunk person in the street zigzagging, and it is predictable in a way. It's predictable that you cannot trust what he's going to be doing next. And that when you are a human walking in the street, it tells you, okay, keep your distance, increase clearance, or do a larger maneuver to avoid collision, for example. No? So have you considered other measurements that could also include that kind of predictability, a bit of a more chaotic predictability, to say somehow? Does it make sense?
Sure. I think, again, very good question, but it's a little similar to the one that Alexandre asked. Maybe the matter of context, let's say, the social interactions and also the scene context, that can be also taken into account in the predictability. That's very right. Maybe I can give the same answer here. Yes, you can condition this this indicator on other variables such as the interactions. Let's say you can you define a interaction variable and you define a kernel density for that, and you can do the same calculation and find the entropy here. I hope I have gives partially answering your question.
Yeah, no, it is very much related with the previous question by Alexandre. It's true. The kind of example I'm giving you, it's in a way related to interactions. Interactions also cause abrupt changes in the trajectory of a person, you know, because we haven't predicted correctly what the others are going to do. We might end up having to do an abrupt turn, or we might end up having to step backwards, for example, because we are about to collide, right? And that kind of behavior is very difficult to capture with your current metrics, I believe. So if you cannot capture, then you wouldn't be able to reproduce it, right?
I'm lost in the question. Can you repeat the last part?
I can try to rephrase it. I'm saying that there are behaviors in a crowd that are by nature unpredictable, right? And a lot of them happen out of interactions. And if I understand correctly, your metrics that the current methods you're using, they wouldn't be able to capture that kind of unpredicted behaviors. And therefore, if you cannot capture them, then you wouldn't be able to replicate similar behaviors later on, correct?
So in terms of social interaction, if you meant, right, the model here is not taking into account any social context, let's say. And if I'm correct here, you can still, if you have some examples here in your data, and if you can compare these examples with the rest of the data, you can do it. I mean, if you have data for it, and if you can do the comparison with other samples, that's it. And still, you can get some intuition about the predictability of that case.
Okay. Okay. So moving, I think I have a few more questions that I think they've been pretty much covered by Alexandre before. One last thing maybe. The chapter on occlusion for robots, that it's a very interesting problem again. And you are in this work, you're extracting basically the probabilities of having people behind others that are currently occluded. And you introduce this concept of ties, no? That you consider social ties and the absent ties. And by social ties, you take into account, you mentioned, take into account groups, no? People that are working together for some reason. And therefore, those people will be together for a longer period of time. So I didn't quite understand, in order to determine these strong and absent ties, is it done by hand? Is it manually annotated, the kind of relationships? Or are you extracting, or are you identifying strong ties and absent ties automatically?
No, it's like, as I said, very simple rules based on the distance between the agents and the variation in the distance, and also the orientation between the two agents. We classified them, and we got this quite very interesting tool. I mean, it was just kind of find groups of people in a crowd, right?
Okay, so do you take into account time information? So for example, an absent tie, such a collision and an overtaking, typically is an interaction between people that happens for a short period of time. Whereas a strong tie, like group behavior or follow leader behavior, it's a tie that, because those people have some kind of connection, they will stick together for a longer period of time. So do you consider time also to differentiate between strong and absent ties, or you haven't thought about that?
So just to calculate them, we considered a 1 second time window to measure this difference, but not longer than that. And that's why I mentioned in the future work, you can also leverage the machine learning algorithms here to maybe encode the longer trajectories and to find a relationship between those pedestrians. This is something can be done. Okay,
yeah, because about that, if you study, you process those trajectories for a longer period of time, in a way you could extract that information and turn it into semantics, for example, no? Semantic information that could identify at a social level the kind of relationship between those people that might even give you more clarity to determine between the types of ties. I guess, I'm only guessing whether that could be included in the system.
I mean, a lot of related work on human trajectory prediction with neural network. A lot of them, I think, can be applied here using the context, using the semantic information, and a lot of them can be imported here and be applied here. It could be actually a nice direction for the future work.
Okay. Okay. So with that, I will conclude my questions. Congratulations again. Very, very nice work.
Thank you very much.
Thank you, Nuria. So now we go in Toulouse with Frédéric LERASLE, professeur à l'université Paul Sabatier. Frédéric.
Okay, thank you, Eric. Thanks also to Jean-Bernard and Julien for the invitation today. I would like also to, of course, to congratulate Javad for your pleasant and convincing presentation today, and the large amount on development and the numerous and distinct contribution you have performed during your PhD. So congratulations. Of course, I have a few questions, or perhaps general ones. First of all, I would like to come back to a question. I think this was a question from Dinesh, because in the document and also today, you speak about crowd on large group of pedestrian, but this is not clear for me how many people are present in the scene, assuming that your algorithms are supposed to be efficient for a certain pedestrian density, meaning I think you need to have not too many or too few agents in the scene, right? So my question is about the how you can quantify what is the limit in terms of congested human-centered seed or uncluttered seed your algorithms can deal with. You understand my questions?
For which part, if I understood well, for the prediction?
I speak in general. For instance, for the two approach social ways, and probably also for handling occlusion. My question is, what range of density, meaning a certain number of people in a certain space, your algorithm deal with. You understand?
Yeah. Very good question, actually. And okay, to answer your question, I have to get back to the study that we did on the data sets, where we observed meaningful differences on some of the indicators for different data sets. For example, for a high density crowd and a low density crowd, mid density crowd. So we have different properties and different even non-linearity of the trajectories and so on. And that's why I cannot say the social ways model can be a generalized model to work on any type of environment with any type of density or any level of density. And this is a big issue with a lot of prediction models that are there today. So for this, first, we have to have data. There are some efforts to collect data, of course, like the one that was done by Alexandre to collect a very large scale crowd data set in Lausanne. But we need a lot of similar data collections within different environments with different type of activities. And once we have those kind of data, we can train more generalized models. Now, for now, for social ways or for other models that we showed here, just let's say very limited tests on ETH, UCY, and Hermes dataset, they are very limited and small data sets. Of course, it's not enough for deployment in industry, of course, but yeah, that's the answer I can give to you.
Okay, but just to precise my questions, we could imagine that we can measure this density and try to adapt the algorithms consequently. You know, for instance, there exists some works in the literature in order to measure this density in congested scene, and perhaps with such measurement we can deduce the best way on how to adapt in, I would say, in real time the algorithms.
Right. We didn't do that, but this is a very interesting direction for the future, to transfer models from one environment or from one type of data to another. This is very interesting. It's not there. This was something at some point I was really looking to work on this, but I had other problems to work on. But this is a very important question actually here. Our robot is working in an environment, is doing the prediction here in this corridor. Next move to another corridor in the same building with higher density crowd, with maybe other type of people. Here, maybe it has to be able to deal with this new type of behaviors, but it's not there. I'm not aware of any research about this, but I think in the future this is one of the main directions to follow.
Okay, thank you. Another question, which is in the same vein, is in your algorithms you have, but this is normal, you have a few free parameters, meaning the parameters that you have to tune empirically, I suppose, but you don't say anything about that. Meaning, for instance, if I remind me clearly, you have a spatial clip, a temporal clip, and so on, and some other free parameters. My question is, how do you tune such parameters? You do it empirically, or you know that there exist some methods in order to tune the parameters optimically? So how you do that?
I just didn't get the parameter that you named. Can you repeat, please? Which one?
For instance, it's just an example, but if I remind me clearly, in the chapter 3, the chapter which is called opentrage, you have some free parameters like lambda, k, r, but this is just an example, because I think for the other approach you have also free parameters, but this is normal, of course. So the question is, how do you tune such parameters? Because I suppose that these free parameters have some impacts on the performance. So
yes, right. I'm not exactly sure on the amount of the parameter that I just tell you. For some of them, we use the related work, of course. For example, for the density, this lambda parameter. So the density is not something that proposed by ours. It's like from another paper, and we use those values in the original paper, in the original work. But the thing is, for this chapter at least, there are indicators, and let's say any value that you pick for the lambda, of course, it can impact the outputs, but still it is some indicator. So it's not like a metric to say it has to it may make a difference. I mean, for a metric, the story will be different, but for an indicator, of course you can use some non-optimized parameter, anything. Yeah, a lot of those parameters are there in the codes, in the source codes that we implemented. They have to be also reported maybe in the paper, in the work, in the thesis as well. But yeah, that's the answer that I can give.
Okay. Okay. Another questions without any link regarding the perspective. If I noticed correctly in the manuscript, I don't think so. You have mentioned this point today, but you mentioned the new scene dataset for further evaluation, right? I think it is in the perspective of the manuscript. And as you know, the new scene dataset is completely different because this dataset corresponds to road scene with pedestrian, of course, but also some other kinds of agent, meaning cars, trucks, motorcycle, bicycle, and so on. So my question is, but perhaps this is a difficult question, is how to extend your works to such heterogeneous multi-agent scenario? Because I think we have to take care about some other aspect, not especially the social ties, but we could imagine that we must take care about safety behaviors or something like that if we consider urban scene with traffic and so on. You understand my question?
Yes, yes.
So my question is, how could we extend your the different concept that you have developed in your work to such a scene, to such scenario?
So, yeah, very good question. And I am aware of some works here. For example, on the, for tackling different types of agents in an environment, there are some work here. One is from the team of Dinesh, who is here, that they also picked some interesting data in India from very different type of agents and even animals, as far as I remember, in the streets, a lot of things like this. So what is done in related work is that to handle this interaction between different types of agents, that's maybe a different thing. I mean, we cannot make the same assumptions that we did for the social ways, that the interactions between human cannot be, of course, generalized between a human and a bicycle or some other road user, So this is something to deal with different types of interactions in different ways. I know there are works here. There are some related works here, including, as far as I remember, the trajectory plus that handle different types of agents, and in a graph neural network. Yeah. Actually, it needs quite some adaptations and modifications on the system to be able to predict in those scenarios with different types of agents, including vehicle, bicycle, pedestrian, and so on. But at the end, let's say at the beginning, our goal was to develop these social ways for human populated environments, because we had pepper in a crowd, maybe not a lot of other types of agents, maybe just people. And that was the motivation that we implemented social ways. But you're right. If you want to deploy it for last mile delivery robots in the street, yeah, a lot of other road users has to be taken into account.
Okay, perhaps a last question. This is, I suppose, a quick question. I love your taxonomy. I think this is the slide number 12, but this is not really important, in which you characterize what you call a knowledge-based approach on data-driven approach. So, for instance, for knowledge-based approach, you have developed probabilistic ones. For data-driven approach, you have developed GAN ones. And so I think this categorization is good. My question is, do you think it could be interesting to mix the two different classes of approach, meaning we can imagine that we have an inference based on a data-driven approach, and we fuse, for instance, in a late state fusion strategy or level with a data-driven one. You think we can improve the results, or what is your opinion about that?
You mean to mix different models?
Yes.
If I understood well?
Meaning probabilistic ones with associated outputs, for instance, and on the data-driven ones, and try to mix the two inference in order to improve the results. But I'm not sure it will be the case. But please give me your impression about this idea.
So if I understood correctly the question, if the point is about mixing different types of approaches,
yes,
some related works are already there. For example, is crowd models that are taking into account the social interactions with reinforcement learning. There are some work here, of course, so I'm aware of some of them, or crowd models with neural networks. This is, let's say, still some work here. I mean, you can raise a lot of questions about this map here. You know, it's just like giving some intuition. It's not very correct. It's not very accurate, let's say. I mean, in the survey that published by Fantol and PETTRE, the student of Julien, we saw a much broader range of approaches for the crowd models, including very recent. I mean, they can be extended to very recent data-driven models, right? These crowd models here. So there are works here, of course. They have already been there has been already some integrations between those categories. And also one of the contributions in our work was to introduce some of the handcrafted social features in the neural network. And that was kind of something that we used in social ways. But still, I really like this type of perspective to combine these experiences from different approaches, from reinforcement learning. There's been a lot of research from neural network, from planning-based models. So yeah, I think we can leverage on the combination of these models and make better and more robust models here.
Okay, so one more time, congratulations for all your works, Javad, and thanks a lot for the response to my questions. I leave the floor to our president, Eric.
Merci, Frédéric. So I will ask one or two questions now before giving the floor to Julien and Jean-Bernard. I have not a lot of questions because crowd simulation is not my really my topic. But yeah, when you speak about occlusion prediction, I don't remember. It was in 36, 7. I don't remember exactly. Yes, this one. Perfect. This is this one. Actually, the prediction is done by a recast. So very simple questions. First, it's a recasting for simulating
Yes.
the basic stuff. Okay, but you simulate from only from the perspective of only the robot, the pink circle,
Yes.
or also from all the other characters. To see
For this
yeah,
frame, yes, on the robot, but
because the other has the position of the robot will have an impact on the trajectory of the others. And do you also the other are actual one, or I don't see a real one.
So yeah.
It's real people, or it's in simulation. Do you also simulate the same thing from the other from the point of view of the other characters? Or?
No. They are just replication of the data, just trajectories of the data.
Okay.
So yeah, there is some question here why you didn't simulate, you didn't consider the impact of this agent here. But I mean, the problem here was to more think of the occlusion that is seen by the robot, right? You know, we assume that we have a robot almost just like a person in a crowd, and then it has its own sensors, and there is some occlusion to deal with.
Okay, and when you predict the HTC, that's it. Do you use some kind of perception to predict the trajectory of your character, or something? Okay.
I'm not sure if I understood.
Okay, no, don't worry. When you have the robot in the crowd, in the at the end, you say it is controlled using some kind of joystick. Is it a classical motion? I mean, a realistic motion, or do you try to perturbate the crowd in some way, or is it a realistic one? Or
there were no intention to perturbate the crowd. Actually, yeah. I mean, maybe the person who was controlling it was not expert, but yeah, the intention was to have a let's say target for the robot. The target point was clear, to navigate from this point to that point, just this. Yeah, that was the goal here.
Okay, so I will not ask more questions. So Jean-Bernard, si tu as des questions ou des remarques.
Of course. Hello everyone, greetings from Mexico, from Guanajuato. Yeah, well, I shouldn't ask questions, right? but yeah. Anyway, I will do some comments, or high-level comments, or questions, more philosophical questions, maybe to Javad. First, Javad, I just want to stress that. Well, it has been really a pleasure to work with you. I really enjoyed it until even if it was at a long distance relationship for some time. It was really enjoyable from my side. So thank you for all your work. Congrats for the presentation. I think it sums up well your contributions. Just a few comments or questions. To start with, sorry, it may put I don't know, put into question the whole work. But if you come back to your slide, I think the slide 1 or 2, maybe 2. If your aim is to, if the
One
aim,
is the
maybe 2. I think the slide where no 3, 4, no, yeah, this one
3.
I think. The one where you have the chain starting from I don't remember, like perception, prediction, action. Yeah, this one. Yeah,
Yes.
yeah. Here, to be the advocate of the devil, I could say, is prediction really necessary in this context? I mean, don't you think that it could be possible a priori? I mean, theoretically, to learn how to connect directly sense to act, and do as if the prediction was something that be kept internal to the robot or to the machine learning system. I mean, if you, after all, if you sense enough from what has happened just before, you should be able to make abstract the notion of prediction, of plan, and so on, and maybe just to learn how to act from what you sense.
Yeah, very important question, and also something that can question all the work here. Right. There are some efforts here also, as we know, about doing reinforcement learning, which is to not have a prediction component here, to directly learning from sense to act, to, let's say, plan, at least. So reinforcement learning can be an answer to this question, where we don't need a prediction. But I think still, in a lot of applications, this prediction can be important for other reasons, such as interpretability of this system, or let's say, we need to have systems that explain why they are doing this, explainable machines or something like this. And that's why we cannot just learn a machine to learn a state, to an action, and without any reasoning here, and send them to the streets, and without any considering about what will happen, if they are really take care about other agents, the prediction of other agents or not. So that's why still, if you want to do some other methods, still we need this kind of prediction. I think this is the answer I can give to you.
Right, I think it's a good answer. I mean, yeah, that's a good justification for keeping prediction and planning in the loop, I guess. Yeah. Also, taking advantage of this slide, in fact, with the image on the right, and maybe as a follow-up, I think it could be a follow-up of Eric's question, for this special context of pedestrian motion prediction from the point of view of a mobile robot. Typically, the kind of perception that you have, and from which you can base your prediction model, could be much richer than only the consecutive locations, right, of the pedestrians. In much of the systems you work with, the raw input you are working with were successions of positions. But for example, if you consider image on the right here, the robot and the pedestrians around him, you could think, for example, in using the appearance from the videos, right? Do you think it would be easy, or there could be some way in extending social ways, for example, to rely on image cues, video cues, information about posture, and so on?
Sure, of course. Something that is not taken into account in social ways is the context from a scene context and also other contextual information, such as you said, the appearance of people and so on. I'm aware of some of the work, like in some of the works of Alexandre, for example, who they are doing this pose estimation that also can be helpful for predicting the trajectories. Yes, other inputs to the prediction model can be helpful. And also, yeah, something to consider here is that, if you want to learn those models, of course, with images, we need more computational power to train the system and also test them on the robot, right? Actually, we don't, I would say, have access to those big computational resources, such as big companies that are doing good works here. I mean, as you look, a lot of big works here is done by Google, Facebook. Those have very good resources for training on videos and images and so on. That's not an excuse here, but I think, yeah, just to answer your question again, of course, it makes sense to use other features here in the environment. It needs more complex systems. It needs more money to buy those systems to train those models.
Right. Maybe as a follow-up of one of Alexandre's questions, if I think it's slide 31, the slide where you have the results on the toy datasets from different GAN variants. Yeah, this one. I mean, one of the comments of Alexandre was in the direction of having all of these GAN versions here tested in the same way, and let's say with just one occurrence of each system, right? And with the mode collapse problem visible in most of these cases. I was wondering, maybe it's more here a comment than a question, but maybe to be more fair in the exploration, I mean, of the capacities of all of these models. What about having kind of ensembles of models? Ensemble of models trained, where each of the models could be trained independently from several randomly chosen starting points for the weights, and seeing maybe it could be more expressive to do something like that, to explore a bit the weight space of each of these models, and see if this kind of result that you get here with mode collapsing or the model keeping its mode, it's something which occurs frequently or consistently, or it's just a question of bad choice of bad starting point for the training, for example. You see what I mean?
Not
For each of the model, instead of doing just one training, starting from some maybe randomly chosen parameters, randomly chosen weights, sorry, for the system, and train it. Maybe you could do a kind of ensemble of each model, like I don't know, 10 instances of each model, so that you could have a more so you would have like 10 instances of each GAN with different weights at the end, probably different local minima of the train system. And here you could explore a bit more, the behavior of the system, and not depend too much on one specific training that you would have done. You see what?
So, if I understood correctly, so it's just a matter of weights and the training. So, why the same model? For example, imagine the vanilla GAN that has trained over different iterations and possibly has been in different states regarding its weights, is giving different outputs, but at the same time it's still giving unimodal outputs. You know, I'm not sure if you
if you just repeat, but with a stochastic component, so you just change, for example, the initial weight, and if you repeat some training phases, like I don't know, 10 times and so on, and see how are the results for example vanilla GAN. Maybe it could tell you if this what you have here is just an accident or something that happened consistently and so on.
Yeah, right. One answer here is that it might be so if you mean that, for example, we can have multiple vanilla GANs, each is giving a unimodal output, but if you merge them at the end, you can have multimodality.
Yeah, no, I wasn't speaking about merging them, but that's something that maybe you could do, by the way. I mean, to reach a multimodality as an example. I was just thinking in using it as a way to see if with one model you can keep the multimodality. But yeah, that's also one idea to explore.
But the point I want to make here was, again, there is a problem of, I have to get back to this slide here. Yes, the problem of mode collapse here, actually, right? So, or you know, to averaging to modes. So the thing is, for example, here, there is no guarantee that this. So you know, you can look at this output. It's not similar to none of the modes of the ground truth distribution. So it means that if you consider this as one of those instances in your ensemble, it can also give samples out of the ground truth distribution. So we can maybe stack some unimodal model on top of each other, get some multimodal systems at the end. It's quite interesting idea, you know. And yeah, but still we need to think of something more robust, and I mean, this was something that was achieved by the InfoGAN that we presented, right, in the social base. So yes.
Okay, and maybe a last one. It's about your the last but one chapter, I think, the one about crowd imputation. Here, one aspect I think that is missing is I mean the temporal aspect, right? I mean the temporal consistency a long time. Yeah, how could you cope with that? I mean, how could you accumulate the evidence that you have about your strong sites, absent sites, and so on, community? How do you think you could adapt your current algorithm to not to redo all the work or most of the work, let's say, at each frame, but to accumulate the evidence along the sequences.
The question itself was not clear to me. Can you repeat this, please?
That whether if I'm remembering well, maybe maybe I'm wrong. But I remember that for this part of the work, you most of the reasoning was done statically at one frame, right? At just one frame. And
yes, and also, as I said, a time window of 1 second to calculate. This. Yes.
But the imputation, for example, was done. It is done independently. I mean, for each frame, right? How do you think you could let's say accumulate evidence a long time for having more consistent estimations a long time?
Yeah, very good question. You know about this probability here. You may maybe it's your question, right? You know, we can. I mean, one of the simplest ideas is to have some memories here to remember. If I'm correct, you mean about the previous ties in the same scenario, for example.
Right. Yeah.
Yeah, you can think of like I'm lost in the exact question that I have to answer here.
So we can maybe we can talk about it later. No problem. Yeah.
Take it offline if you prefer.
Okay. I think that's all questions for me. Thank you very much, Sabad. You were on.
Merci.
Thank you, Jean-Bernard.
Merci, Jean-Bernard. So the last one is Julien PETTRE from INRIA.
Okay, thank you, Mr. President, and and thank you, Jean-Bernard, for giving a taste to the jury about how was the PhD meetings during these 3 past years. I will not ask you questions, Javad, just make some comments about how your PhD went, according to me. And first of all, I would like to say that the PhD didn't go exactly as expected. let me remind that you were part of a European project called Crowdbot, where that funded your PhD, and you had to deal with a number of objectives that were set before you came. But this is generally the case for PhD, so that's fine. But what you were supposed to do first was to deal more with the data assimilation problem, which means take those crowd models that we are used to use in the team, and more base your prediction on this kind of tools, with the problem of adjusting their parameters given the observation of a robot. It took you a bit of time to explore this problem, and you came back to me with the conclusion that was that we should not use this kind of approach, but more rely on data-driven kind of approach that were more recent and in the air at the moment. So, yeah, I thought that was kind of a surprise to me, that very early in your PhD you had a clear view about what should be maybe what could be a more promising approach, and we had a couple of meetings discussing this option, and you in the end convinced me, and you explored this way more, which delayed a bit, and this is maybe why it's not really there in your work. It delays a bit to prove the benefit of doing prediction on robot navigation. And maybe I can say here that this is something you are working on right now, and we try to come as a conclusion, a last result in your PhD work, to demonstrate that all this has a value for robotics, of course. So you explored different paths, and maybe you were lucky about two things. First of all, so you started your PhD where there was really a change in the field of crowd simulation, really moving from handcrafted model to more data-driven ones, with a convergence with the computer vision field, giving ideas and solutions for that were probably new to the field of crowd simulation. And also you were lucky because Jean-Bernard Hayet was at that exact moment, he was having a sabbatical in the team, which means that you had all the scientific support to explore this novel idea. But yeah, I think people are not lucky. They are more opportunistic. So they take opportunities when they come to them, and they are capable of catching them. And I think this is what you did. So all this work, all these results you had, I had to take you back to the initial project work plan. And this is why maybe we have opened many doors and maybe not closed completely all of them. So that's maybe something I hope you will be able to address in the future. But yeah, I think you were not lucky. You were brilliant in taking the good opportunities when they came to you. So this is what I wanted to add, and really insist on the high quality of your work, especially that you are probably the most autonomous student I knew in the many I had the chance to advise. Voilà. So thank you, Javad, and now we will deliberate on your case and see if you get your PhD or not. Yeah.
Before the deliberation, I have to ask if there is a doctor in the room who wants to ask a question. Non? Ça tombe bien. Eh ben, je vous demanderai de sortir.
Yeah. Now we will have
And look at the camera.
Yeah.
Okay, so Javad, Javad, you defended the PhD in computer science. Your contribution and concern with the field of human trajectory prediction to enable mobile robots to navigate in crowded environment. You contribute on various subjects, data set for metrics analysis, model preserving capability in GAN-based prediction, HTP for robot from robot perspective, including predicting occlusion crowd. Every contribution was actually published in a relevant conference or journal. The committee member have considered that this work as inspiring, opening up interesting problem in the field of crowd simulation and analysis, and you do that in a very short time, according to the numerous contributions you got. Through your oral presentation, the committee member appreciated the important contribution, and your presentation was very clear, well illustrative and comprehensive. It was a good balance between technical insight and accessibility. The answer to the numerous and thorough questions of the defense committee member were argued, and you were able also to acknowledge the challenge in a very scientific way. You show that you are very confident in this exercise, and your answers reflect a deep understanding of your research. According to that, for all these reasons, the Defense Committee decided unanimously to award you the degree of Docteur de l'Université de Rennes 1, mention informatique. Congratulations. So I'm not supposed to now, but I will do it with pleasure.
Thank you very much. Maybe I take this time to say a few words about thanking the people that are here and some that are not. Actually, the thesis would not have been completed with the help of many people, including Julien, who is here, my supervisor, who helped me a lot, who was completely supportive during my PhD. And so he was the first one that gave me this opportunity to do a PhD here, and he did all the support for my PhD. And Jean-Marie, also my co-supervisor, that gave a lot of insightful expertise for my PhD. And I never forget the sleepless night before the deadlines that we were working for the submissions. And also I would like to thank my committee, including Dr. Alexandre ALAHI, Dr. Dinesh MANOCHA, Dr. Nuria, PELECHANO, Dr. Frédéric, LERASLE, and Dr. MARCHAND for the time and all the insightful comments that shared with me. I have also I have to thank my friends in the CrowdBot team at Rainbow, and also my friends here, my Iranian friends actually, part of them are here. I really owe to them, and I don't forget all the fun time that we had together here. And I also have to thank my family in Iran that did a lot of things here for me to be here at this point. And I never forget their help and support during my life. And actually my parents who are not here. And also my sisters and brothers, and actually my sister that is not here among us this year because of the COVID. Many thanks to Marzia for all the support. And yeah, the rest of my family, and I never forget all the support that I received from them. I wanted to dedicate my thesis to my sister and also all the people that we missed because of the COVID this year. Thank you.
Okay.
So again, congratulations.
Thank you very much.
Again.
Thank you.
Let me add that it's sort of a double congratulation we have to say. You had two PhD defense in 2 days. That's huge. So I guess that starting from now, you will have a bit of rest.
Yeah, thank you, Julien. Thank you very much for all the help, mostly for the recent rehearsal, all the meetings we had. Yes, thank you very much.
Alexandre, that was a pleasure working with you, and I think we can thank everyone now, and especially Julien for broadcasting this, and maybe we can stop the broadcast now. Thank you very much.
Yeah, thank you, Julien.